Welcome to my YouTube channel. In this video we are going to be looking at the Venturi meter and how it is used to measure the speed of fluid flowing through the pipe. Right, so let's look at a typical diagram of the Venturi meter, which is giving us this. So in this case we're interested in calculating the velocity at this point, the fluid velocity at this point. So there is this contraction at this point where the area at this point 2 is different from the area at this point 1. So at this point we have P1, the pressure here, V1 and the area here. Then at point 2 we have P2 here, A2 and the V2. So in this particular system we are going to be using the Bernoulli's equation to determine the velocity at this point. And the Bernoulli's equation is giving us this, where this is the pressure, density of the fluid, gravity, the height, right, plus half of density times the velocity of the fluid equals to a constant. So that means this parameter at any point in time is equal to this same parameter at another point in time. So instead of writing it in this way, we can also re-express it as this, so that at any point 1 it must be equal to point 2. So the conservation of it's more or less like the conservation of energy equation, right? So if we look at this particular system, you notice that at point 1 and point 2, the height from somewhere here to this point is also equal to from this point to this part, and that's giving us h1 and h2. h1 is this height from the ground to this point, and h2 is from the ground to this point. They are of the same height, so if h1 is equal to h2, so we expect that this will cancel this. So the parameters at the various points are giving us a1, p1, v1, also a2, p2, v2. So since we have established that h1 is equal to h2, and we have seen that the parts that will cancel out, we've seen the part that will cancel out, then the final equation will reduce to this, where this one is a p1 and p2 at point 2, right? So it means that the velocity at point 1 will be different from the velocity at point 2, the pressure at point 2 will be different from the velocity at point p1. Okay, so if we simplify, we have this expression. Now since we're interested in calculating the velocity v1, we have to find a way of replacing v2 in terms of v1, since v2 is not known. And from this point we use our continuity equation, which is giving us this, where the amount of volume flowing through a point per second is equal to the amount of volume flowing through another point per second, right? So if we make v2 the survey formula, we can have v2 equal to a1 over a2 v1. Then by the time we replace this v2 with this inside this equation, we'll have this next expression. Okay, so we now have this expression. We can factorize v1 squared out, and that gives us v1 squared, leaving this one behind, this and this. Now sometimes we might not know the pressure at both points, so we can find this pressure P1 and P2 in terms of another parameter. While in some setup, P1, there will be a gauge at P1 and there will be a gauge at P2 that will measure those two pressures. So once you know the pressure at P1 and P2, you take the difference, you make your V1 survey formula. But in a situation where the pressure gauge is not fixed, or is not the device that measures pressure is not at those 2 points, that's those 2 pipes, then you can replace your P1 with P2 with another expression. Okay, so let's come back. Let's see how we can replace our P1 and P2 by another parameter. Now the pressure at this point is giving us rho gh, which is this height, rho gh, this height, plus the atmospheric pressure, while the pressure at this point is giving us rho gh plus the atmospheric pressure at this point, right? So that we can have an equation like this. For P1, rho gh, this h is the height from this point to this side here, while P2 at point P2 this H2 is from this point to this point. Now if we take P1 minus P2, it will reduce to P1 minus P2 equal to this expression, this everything here minus everything here. This one will cancel this, leaving this and this. So we have P1 minus P2 equal to this. Now we can factorize our rho g, and that gives us this part. So H1 minus H2, that's this height minus this height, will give us this height y, which is P1 minus P2 equal to rho gy. That's this y here. So it's important to know how to get that h. Alright, so anywhere we see P1 minus P2, we replace with this parameter. Since these parameters can be determined easily, or they are known, so we can substitute this value back into the where we are coming from, which is rho gy instead of P1 minus P2. So at this point we can send this one to the bottom. First of all, we took these two to this part, rho cancels rho, and we have v1 squared into bracket all this expression. And if you make this expression v1 squared the subject formula, you'll be having something of this form, right? We can resimplify this one and it gives us okay, I think that's okay. Then let's now look at the next expression, which is the flow rates, how to measure the flow rate using the Venturi meter. Okay, so we still fall back to the Bernoulli's equation. Venturi meter to measure the discharge rate of fluid, or the flow rate, that's the amount of volume that comes out of a pipe per second. So in this case, we still cancel this part and this part, and that gives us this. And taking our P2 to this side, we have this part, right? And we can factorize, but we also have discovered, or we have shown, that P1 minus P2 equal to rho gy, which is equal to this. Then we have rho gy equal to this part, okay, which is also giving us this, because our rho cancel rho 2 come in, we have this one. Now at this point, we're interested in calculating the amount of volume that comes out of the pipe per second. So we no longer need V2 and V1. So, but we know that there is an expression for the flow rate, right, and velocity, which is giving us Q, which is equal to V1 A1 or equal to V2 A2. This formula is a continuity equation that tells us that the amount of volume coming out of a particular point is equal to the amount of volume coming out of a particular point per time. So we can make V1 the Soviet formula and V2 the Soviet formula, and we have this expression, right? So wherever we see V1 and V2, we can substitute with this expression. So at the end, we still come back to this our equation, because this is where we stopped. So if we substitute, we have Q2 equal to, because by that time when we substitute, Q will be common in both and we'll factorize, and at the end we have make Q subscribe the Soviet formula, and that gives us 2gy all over this expression. We can simplify this one further, and that gives us this one if we find the square roots. Now a1 squared, this one is the same thing as 1 over a1 squared, 1 over a2 squared, a1 squared minus this, a2 squared minus this, and that gives us these parts, right? So at the end of the day, this is our charge flow rate for the system. Once we know the area for the first point, we know the area for the second point, we know the y difference, we can calculate the amount of volume that comes out of the liquid per time. I hope this helps. Please like, share and subscribe to this YouTube channel. Thank you for watching.